Hi, RDBury here. Um, Welcome to the third in my series of interesting arithmetic or strange arithmetic. Earlier, we in the previous two episodes we talked about the golden ratio base or finary or base phi, and the upshot for what I want to keep in mind for this time is there was a magic formula that's basically said that the base squared is equal to the base plus 1, and you could summarize that by just saying the base squared minus the base minus 1 equals 0. So it all fits nicely into this nice little row there. And when you expand out the numbers from 1 to whatever, you get this interesting little pattern here. And the special thing about this base is that all the whole numbers and all the fractions of ratios of whole numbers, i.e. the rational numbers, they all have either a terminating decimal or a repeating decimal, just like you have in whole number bases. So what I want to do today is find three more of this type of special number. Now this is a quadratic equation: x squared minus x minus 1 equals 0. So everything I'm going to do today is also the solution of a quadratic equation. And what I'm going to do is the ones that occur between 2 and 3, rather than this one, which is the only one that occurs between 1 and 2. So the first one, the magic equation here is x squared equals 2x plus 1, or x squared minus 2x minus 1 equals 0. And this turns out to be the equation of something called the silver ratio. So I guess it's like the golden ratio, only not quite as good. It's still pretty special, but not quite as special, I guess. And over here, you get another picture of what the numbers look like in this base. The number is bigger than 2, so this base is still 2, but everything after 2 starts getting more interesting. And you have this kind of situation where the decimal, even if you have an integer, the decimal, there's a decimal to the right. And again, there are, I mentioned earlier, there are in base phi, there's some interesting patterns in this. When I write them out like this, for example, if you count runs of ones and zeros, you get only specific numbers in each column. And the same thing happens with this. We'll get, for example, this column here has 3 2s, and it will always have 3 2s in a row, and it will never have 2 or 4. And same thing for the number of ones, only it switches up a little bit. Let's see, I guess, yeah, this one you always have runs of 6, followed by a row of 3 ones. And then the zeros occur in different sets. So this is a set of 5. This is a set of 11. So in that case, there's 2 possibilities. So it does look like it kind of repeats, but it doesn't actually repeat completely. And no matter how long you go, you can't actually get a repeating pattern. But it will almost repeat. If I start out with a certain finite length like this, I can always find an infinite number of those of this same pattern further down. And again, it kind of has this similar pattern on the right. The one thing you might notice here is that it always extends the length by 2 each time, but it only does it about half as often. So on this row, it extended it on the left and on the right both times, but this time it had only extended it on the left. So there's a bunch of interesting patterns with this one too, and I think they're slightly more complicated but very analogous. Now, I won't go into a lot of the details of doing arithmetic in this base like I did with base phi, but it's pretty easy to work out. Once you know, once you've seen the base phi stuff, you can kind of figure out what you need to do based on this rule here. And you also need a rule for which digits are allowed. And the rule in this case is that you're only allowed 0, 1, and 2. And in base phi, you also had an additional rule that you can never have 2 1s in a row. In this base, the rule is every 2 has to be followed by a 0. And that's all you need. If there was a 2 followed by anything else, then you could do a carry. Or if there was a 3, you could do a borrow to get a 2 into the next spot, and then do another, and then do a carry after that. So it works similar to the way base phi works. Now the next highest one is base Phi Squared, and I've got that. Let's see, here it is. And the magic rule for that is that Phi squared minus 3 phi plus 1 equals 0. Now this is a bit different, and we don't have that minus 1 there anymore. We have a plus 1. And you can see that kind of affects things a little bit, because what happens now is that when you write them out, all the digits are all symmetric. So you have this kind of symmetry going on from left and right. And that's kind of how you can tell that something is an integer in this base. I mean, you have rules for divisibility by 3 in base 10. You just add up the digits and keep doing that until you get just 1. And if that one digit is a multiple of 3, then your original number was a multiple of 3. Well, here we have a rule for divisibility by 1. In other words, it's divisible by 1 if it's a whole number. And the rule is if it has these it has this symmetrical pattern. If it doesn't have this symmetrical pattern, then it's not a whole number. And yet again, we have the same kind of pattern with the runs of digits in the column here. In the first column here, we have 3 1s and a 2, then 3 1s and a 2, and then a 1, and then 3 1s and a 2, and 3 1s and a 2. So it looks like the 2s are always preceded by 3 1s, and then the 1s themselves, well, they're a little bit more tricky to pin down. So sometimes the patterns are kind of fixed, and sometimes they're not. Now, what I said earlier about there being a rule for when a number is an integer, well, you can notice if you look carefully with this silver ratio base that the integers do some things that are different than what you can see some actual patterns in there that weren't there in the golden ratio base. For example, for this column here and this column here, the 1s are always in the same positions. The 2s and the 0s don't seem to work that way, but the 1s are always in the same places. So you have 2 1s here, 2 1s here, 2 1s there, 2 1s there, and 2 1s there, and 2 1s there. Now that only seems to work for the odd places from the 1s column. So it works for the first column to the left and the first column to the right. Let's try the third column to the left and the third column to the right. And you can see that again, it's the same thing, that the 1s are always in the same places. For the second column and for the second columns, it doesn't work that way. So there's other kind of more subtle patterns you can discover, and kind of knowing those, you can kind of find similar patterns in the base phi representation. So more interesting patterns to discover. And finally, let's get to the last number that's between 2 and 3, which is this one. This has the magic formula here is x squared equals 2x plus 2. Now this is actually equals square root of 3 plus 1, which is slightly less than 3. And I look at the numbers over here, and now it looks a little bit different on the right side here. We don't get this kind of, more or less symmetrical pattern here. The right side is expanding a lot faster than the left, and there doesn't seem to be any matchup between when the left starts and when the right stuff starts, like there was in the other bases. And that pretty much has to do with the fact that there is a 2 here and not a 1. I mean, you could have anything that's if you have a 1 or a minus 1, then the left and right are more or less the same length, but when you start having a number which is in either less than minus 1 or bigger than 1, then the numbers on the right start getting larger faster. And another thing that seems to go away is our integer divisibility rule, our divisibility by 1 rule. That doesn't seem to work in this case. The rule about the number of individual digits here, well, that's if it exists, it's kind of more complicated than I'm willing to try to figure out. I mean, in this column here, we've got 3 1s and then 3 2s and 3 2s, or 3 2s again, and now here are 5 2s. So it gets kind of weird. So those initial ones that we talked about, those are kind of exceptional cases, and this is more of a typical case. So you have to be careful when you look at the first few examples of something that the patterns you see may only be applied to those examples that you've looked at so far. And when you start looking at more general cases, that those patterns may fail to appear anymore. All right, well, so we don't have the rules about the number of digits in the columns like we did before. At least if they are there, they're a lot more complicated. But we do have another interesting pattern in this case, and that is if we look at how these decimals end. So once we get past these first few here, they all end in 1102, and it gets to be kind of annoying that you have the same pattern, and then the digit before that is either going to be a 0 or a 2. You can't end with 11102. And then before that, well, it looks like the 2, if you have a 2 there, or if you have a 0 there, it could be followed or preceded by a 0 or a 2. But if you have a 2, it can only be preceded by a 0. Actually, it could never be preceded by a 2 anyway, because then you'd have two 2s in a row, which we'll get into in a bit. But it can't be a 1 either. So, and here you can't have a 101102. It has to be 0 or a 2. So there seems to be a definite, a small number of patterns that you can get at the end of a decimal when it's an integer, which doesn't happen with the other ones we've seen so far. So far, whatever pattern matches the general rule can occur at the end, but this one doesn't. It doesn't happen that way. So we lose one type of pattern and we gain an entirely new and different type of pattern. Now, one thing I want to wrap up with is talking about the rule for which digits are allowed in these last two examples. In this one, it's a lot similar to the silver ratio one. It's just that now instead of a 2 having to be followed by a 0, a 2 can be followed by a 0 or a 1, but not a 2. So you can have two 2s in a row. That's pretty much the same as the other examples. But this Phi Squared one, that gets a lot more complicated. In this one, you can have a 2 followed by a 1 or a 0. You can't have two 2s in a row like it's with the other one. But you also can't have a 2, 1, 2. See, every time I have 2 with a 2 spots away, there has to be at least one. There has to be a 0 in there, not at either a 2 or a 1. And that works no matter how long the distance is between the 2s. Here's one where the 2s are 3 places away. And I can't have a 2, 1, 1, 2. I can have a 2, 1, 0, 2 or a 2, 0, 1, 2 or 2, 0, 0, 2, but I can't have 2, 1, 1, 2. And so the same thing happens with 4. So in that case, I can't have a 2, 1, 1, 1, 2. So instead of having just like this one simple rule, you've got sort of an infinite number of rules. And that makes the calculations in this case a little bit trickier. And actually, you know what? I just discovered an error here. I should have been able to carry that. I was kind of just taken by surprise by that, and actually you can tell that this is wrong because it doesn't follow this 1, 2, 1, 1 followed by a single 2 rule anymore. Here I have 2 1s in a row, so that 1 must be an error somehow, and the reason is because it doesn't follow the rule that it's supposed to follow. So what I'm going to do is carry this 2 over here. Now I have a negative 1 in that spot, but that's okay because I can carry again. And I can keep carrying over from the previous columns until that whole thing gets converted into these twos that are certain or the same distance apart as the original pattern was. So that fixed that. I don't think there's any other problems in there, but it makes the arithmetic a lot more tricky for this base than for the other ones. So, and another, I guess, one final thing. I keep on thinking of additional things to say about this one because it is a little bit strange, actually, compared to the other ones. For the whole numbers, you had this kind of symmetrical pattern, and the numbers always stop at some point. But if I look at, say, 2 times the base minus 1, so basically I just want to do subtraction here. Well, how do you do subtraction? Well, you have a minus 1, then you have to do some borrowing there. So I'm going to borrow 1 from there and add 3 and subtract 1 from there. So I get this. And now I've got the same thing here, a 2 and a 1. So let's borrow again. And it just keeps on going forever. So it's like, even though I had whole numbers to start with, I mean, it's not, I mean, it is, it isn't an integer, but at least it was a multiple of the base and another integer. It doesn't stop anywhere. It just gives you a repeating decimal instead. So it's a really kind of a odd system here in that if you add, you're fine. If your original numbers terminated, then the sum terminates. But even if you start with a number or subtracting a smaller number from a larger number, when you subtract, you might get this repeating ones instead of a terminating decimal. So that's a little bit odd, and it's something we should look out for in the other bases, that when you actually do the arithmetic, and let's go back to base phi, that the process actually ends and you get a number that stops when you have an integer. It's not that hard to prove, but it is something that is not immediately obvious that it's true once you think about that it might not be true. So another kind of surprise going on in there. So anyway, I'm going to wrap it up there and sign off. Next time I'm going to be talking about, instead of quadratic bases, irrational bases, I'm going to be talking about cubic bases. So I hope you'll join me for that. Until then, bye.